Where where is Alicia?
I don't know. Hi, everybody. My name is Ethan. This is Drexel's fall term. It is the 5th week, so it's our 5th GBM for this term. For those who don't know, we've been working on our project on predicting the reoccurrence of non-small cell lung cancer using radiogenomics. Radiogenomics is an intersection of image analysis, genomics, and then machine learning. We've been collaborating on a GitHub right here to create reproducible code that will allow people to calculate features and run different functions on the data from our data set of choice. And I'll pull that up right now. Here. And then we've also been collaborating on the paper. So I'm preparing for a conference next week, so I haven't made much progress. I did figure out one thing, and I wanted to talk about that. So there was a question I posed last meeting about extracting features from, no, do not download that, oh goodness, about extracting features from images. And a CT image is, I'll show you what a CT image, when you have a CT image of a torso, there's multiple snapshots at different lengths of the torso. And what we want is a representative features for each patient. Now, each patient has, upwards of 200, 300 images. So the trick is going to be to find the images which best represent, is it the sharp one? Yeah, best represent what we're trying to predict, or best represent the features that we're trying to predict. So there were a couple strategies people have mentioned in the papers I've read. One was to pick the area of the lung that has the largest diameter or largest area. There is a, how do I pan? Is that, no, I want to.
If you want to pan in, use the zoom.
Oh, right here. I'm trying to move through the image. I don't think I think it'll take too long to load. Anyway, so the strategy we're going to use is we're likely going to pick the area of the lung that has the largest volume or largest area, and then pick the two nearest images, so the image before and the image after, and calculate features on all three of those images. That was an approach I noticed. We could do that. We could treat the largest image as the midpoint. This is the, trying to draw. We could treat this image as the mid. If this is the largest area, we could do, 2 before and then the 2 after. And then our feature set for that one person will be composed of all of these features. And I think we have 160 some features for our imaging. We have about 19,000 features right now. We haven't done anything with them. I actually tried to use a random forest classifier with just the genomic features on that outcome, and it didn't do too well. We're also dealing with the fact that we don't have many subjects, which kind of stinks, right? We only have 130 subjects. So we have a lot of features, very few samples. And you can see here what happened when I was trying to do some prediction only using the genomic features. It only predicted zeros, which isn't much of a model in my opinion. So this is going to be tough, right? Because our set is going to be limited. And I think the paper that was, I wonder if we still have that. Does anybody still have that paper that was?
Which one?
I think the one Suhani sent.
Yeah.
Oh, Sushi's. One second.
I think that one will be a good reference for us because they did something similar using what looks to be the same data set.
It's in medical imaging, yeah.
right here. So we'll probably have to use this paper and study this paper very heavily. So if you guys haven't checked it out, I would read it. They also have very few number of patients. I think they have 81. Regardless, we need to figure out to, train a model on such little patients. It kind of stinks. Anyway, so what I wanted to go over right now is the fact that we have a paper to write and we haven't really done much with it. We have a cool name, right? Radiogenets. Maybe if we come up with some sort of novel method, then that'll somehow fit into the name. I don't know if deep learning is gonna be what we're using because of the sample problem, because of the number of samples we have.
Yeah, we could, if you're using transformer, so we could use like transformer learning.
So
Okay.
transformers, can you use them with few samples?
I mean, 121 is like the number of features a lot.
Yeah.
So the input X would be a lot, right? So that's how transformers work.
Okay.
We're gonna weight the inputs according to their correlations and then what given output. So I guess that wouldn't be a problem.
Yeah. So today, unless anybody has questions about the project, it's kind of up to me to finish the code. It's not terrible. It's just me finding time to do it. I might do it tomorrow or tonight, or I don't know. And then
That would be,
sorry.
yeah, go ahead.
But the main point that I want to talk about is the paper, because we really don't have a content on it. Now, it's important to build up references, and I use this thing called SciWheel. I don't know if anyone else has heard of it. Probably people who haven't done papers before haven't. It's a great way to archive articles you read on Scholar. So if I'm on Scholar and I search up, deep learning, I want to learn about deep learning, Goodfellow shows up. I can click this SciWheel button and it'll ask me whether I want to add it to a project. And I have some projects going on, and I could add it to reading list, add, and then I go to SciWheel and I can generate citations based off of any style. They have IEEE, they have Harvard, they have many different things you could use. It's a great way to organize it. Okay, Alicia, you'll start on the introduction tonight. Cool. But it's much more than just saying like we're gonna do this. I want to also talk about specifically. Maybe we can extend this outline because right now it isn't too detailed, which is fine.
Yeah, it's not.
So in the introduction, we're going to want to have a motivation for using radiogenomics, and part of, I'm just going to let's scribble some stuff here. So heading, you have a really nice outline here. I don't want to mess it up. Okay, so for this, what I do want to say is we have to establish, which was better typing, motivation. So this motivation can be for, I think the motivation here is going to be for looking at reoccurrence of non-small cell lung cancer. So creating a basis for why it's important to look at this disease. And so when you might start off with is you might ask, okay, so what facts are there on non-small cell lung cancer? non-small cell lung cancer. I know I think 80% of lung cancers are non-small cell. Cancer.gov is a great resource, something that you'd be able to readily cite, considering it's from the National Cancer Institute. So if they have any metrics or figures, I definitely use those. I'm sure that they have some stuff here. This would be considered a pretty good source. But then also on the flip side, you could go to Scholar and do the same thing. So, but I'm afraid that if you look it up here, it's gonna be a lot of research, or never mind. Like this one. This one looks good. It's heavily cited, so it must be good. And I don't know if I have access to this. I'm sure there's some way we could get access. Oh, there it is. So this review, has a lot about diagnosis, prognosis factors, and probably something that Zavik mentioned. I'm gonna get your name wrong. I'm really bad at pronouncing names apparently.
Yeah.
Sadvik, right?
Yes.
Okay, something that Sadvik mentioned is that a reason why non-small cell lung cancer is particularly interesting is because you said it's normally non-malignant, but then after surgery
No.
it
So they are in generally non-metastatic in nature.
Okay.
Yeah, and it is showing reoccurrence. That is kind of cool. Like not cool for the patient, cool for us.
Interesting. Let's use interesting.
Interesting, yeah. But
yeah,
also,
sure.
when you're writing a research paper, so can you open any paper, Ethan? Like any random, the Lancet one that you were opening, yeah. So if you go down to the any subsections, yeah. So maybe, yeah. So see here. So now when you're writing a paper, say you're gonna reference this paper, right? You're gonna say use some information that they have cited here. So you're gonna write that and then cite this paper. But also see that they have cited these two papers here. So you could look these up and say, if they align with it, you could cross-reference these papers as well. So this is how you do basically a literature review.
I could look at the diagnostic value of these two things, and maybe we'd find that important. And some people say like structuring a report. People talk about this in like writing like lab reports and writing research papers. Whenever you make a claim, every claim you make that's about the background or introduction should have. So the background introduction, every claim you make should have a reference. But any analysis you make is novel to the paper, so that doesn't necessarily need a reference, but it needs to be supported by logic, a model, math, observation, stuff like that.
And then in results, you can again have references about past, what people have done, and how you compete against them. Yeah. So it's like the more references you have in your introduction and background, the chances of getting accepted into a good journal kind of increases, because obviously it looks much better and people get more citations out of it. So
yeah. So, these references establish a motivation for looking at the disease. Since we're dealing with machine learning, we need to look at motivation for other things, right? So our motivation for looking at the disease can be established by these two references and more, but then we also need to establish why we're using a radiogenomics approach. So if we're using radiogenomics, and I mean, there might be plenty of, I don't know if there's papers that discuss why radiogenomics is better. I mean, you could probably look this up for yourself. So if I want to go to Scholar and say radiogenomics, I've never heard of radiogenomics till it was mentioned. So like this one right here, what it is and why it's important. This is a good reference. Journal of American College of Radiology in that journal, that Elsevier. I'm
Xavier or Elsevier.
I'm chronically bad at pronouncing things. It's a curse. To work on that. So this one is a good reference to use. Besides looking at, we tackled for the disease, for using radiogenomics, and then, so radiogenomics is just the aggregate, from what I can tell, it's just the is like the aggregation of data using imaging, using clinical data, using genomics, and then it's the analysis of it. And then the next part is for using a specific model or set of models. And because we don't have a good arsenal of models built up that we can use yet, we need to fill in this later. So we mentioned transformers. I think Dan Schwartz mentioned something, and I kind of want to find out what he mentioned. He mentioned something to me privately. I wish he would talk in the main chat. That goes for everybody. If you can mention something in the main chat other than sending it to me. He mentioned GANs, which could be used to generate more images. I don't know if that'd be possible. Deep learning, we could use sparse coding, but whatever models we pick, we have to kind of justify while we're using them. And this goes back to let's look at deep learning, and let's see why it's important. Oh, go to this book on deep learning. There's probably a section for application, and in which you'd reference that section for application, say it works. Like convolution neural networks are known to be good at image processing. Now we're not using convolution in our right now in our project, because we're not looking at the images directly. What we're doing is we're taking an image cross section and we're calculating these radiogenomic summary features. So like one feature might be, the width. Another feature might be the grain, the coarseness. The idea is that these features capture information that would otherwise be lost or difficult to find in, a convolution net. Also, these features have been handcrafted by people who've studied radiogenomics. So it kind of goes back to the whole idea of creating an expert system. Yeah, that's the paper. You should have access to it, anybody who clicks on the link. So yeah, I think these three things for the motivation kind of are important. Establishing a motivation for the disease, for using radiogenomics, and then for using a specific set of models. What else would you include in the motivation, do you think? I'm asking because I'm not quite sure. Civic?
I'm thinking.
Yeah, if the introduction really should just set up the motivation. It should tell a story, and most papers should read like a story.
Yeah. Also, why not we are going just for the radiology part of it? Why are we going for radiogenomics like this? Hopefully.
Yeah.
And how this could be like a more generalized model that we make would be more generalized than just radiology model, because we are having so many different attributes in our classification process.
Yeah,
I could kind of like
the specific set of models is this generalizable. Yeah. So I think this is a good set of topics to look at for the introduction. For the background, you're expanding off of everything you've said here. So we want to talk about what has been done with, so what has been done, it can almost be parallel. What has been done with, and then the first part would be non-small cell lung cancer. What has been done with radiogenomics, and what has been done with the models we've chosen to use. Right. This background study can be thought of as related work. So if we're aiming to look at these, if we're establishing a motivation for these three things, we should attempt to thoroughly investigate what has already been done with these three things as well. And I've kind of been helping you guys do that by going over, I've read 2 reviews on radiogenomics, and I've talked to you guys about different models, and you guys seem to have a good grasp on what's been done. So it's just about putting into words. Oh, sorry, we have a question. Sorry, I'm a bit confused about the background, what has been done, and what is novel about our approach. Novelty comes.
Can I answer that?
Sure.
So basically in the background, you say what all which has been done, like what is the state of the art right now?
Like related work.
Yeah. Like what are the similar works which are being done right now? And then the novel part comes when you write your method, like what's new that you're writing, or you could include that in your results that, oh, this is the new finding we had. You necessarily don't speak much about your method or result in your introduction or your background, because that is, the fun stuff you want people to read and that keep them hold. Yeah. So you just write about.
Yeah, I'm gonna add these just so we know that we're following the same parallel. It's kind of like when you were in high school when you were writing what was it, a thesis, and your 3 paragraphs in the middle followed the same structure of the thesis. It's kind of the same thing, but we're doing it at a larger scale. So if we're doing this, we should also have. Can I change? I'm going to change this to related work, because I think that, I don't know, that's my preference. So yeah, if you have these 3, you're also going to have these 3 in related work, and that's what you're going to cover. I'm asking what the new things about our approach is. So I'm hoping the novelty will come in with using, the imaging, the genomics, and then also with the clinical data. The other paper we read is the newest paper we've seen out there on this type of data set, and they didn't use the clinical features. They didn't use the demographics. They didn't use the smoking, non-smoking. They didn't use any of that. There's some other things we can do to the genomic data to make it more useful. I don't imagine just throwing 19,000 features from RNA reads or RNA sequencing is the best way to organize that data. I'm sure there's information that we need to still mine out of that matrix. Yeah.
Also, we could get novelty out of, like, if we use new kind of models.
Yeah.
Like if you're using transformers or something, people haven't really used in medical fields. So it's kind of like novel. I don't know.
You can even, what you can do is you could throw sparse coding at the genomic data. That might be something we want to do too. So sparse coding is a unsupervised method that finds a basis to describe a sparse basis to describe a set of features. So if I have a vector, it'll find a representation of that vector in a low dimension. So it'll take that vector and it'll bring it down to a lower dimension. If you're looking at handwritten images, the MINS data set, and you have a 9, a sparse encoding might find one element to be, this leg right here. This might be one element. This might be another element. This might be another element. Because in most sparse coding algorithms, what they do is they base the how well the algorithm is doing based off how well the dictionary elements, are called dictionary elements, can reconstruct the image. So they look at like a reconstruction error. The reason I bring this up is because if we're looking at, a set of genomic features that represent RNA sequencing, and we know that a set of them correspond to like cancer, and a set of them correspond to non-cancer, we might want to find if we can somehow find a basis that describes the expression pattern of cancer, and then compare that to the expression pattern of non-cancer. It should be a C, non-cancer. And then in comparing these, we could use this as a heuristic, not necessarily as features, but as a heuristic. Because I think the features would just be the RNA expression themselves. That's, the novelty is still up for grabs, and whoever comes up with a winning idea, I don't know, I'll make you cookies or something. I don't know. We'll figure it out. Heuristic, right? So if I were to say that like all salmon are, red or pink, or that salmon color, and I use that to separate salmon, that's kind of like a heuristic. Most machine learning models can be thought of as being a heuristic as well, because you're using some generalization. It's just like a rule. It's a generalization you use to separate data. And so when I said that you could use the sparse dictionaries as a heuristic, you can say if once you learn a dictionary for cancer, and once you learn a dictionary for non-cancer, or you learn a dictionary for the cancer that reoccurs and the cancer that doesn't reoccur, what you can do is you can use that to as a heuristic for separating whether or not the cancer will occur or not, and then you can incorporate it into your model. Yeah, heuristics are used like all the time. Like I don't know, one heuristic might be when you're applying for a job, they look at your GPA and say if it's over a 3.2, you're in, or if it's below a 2.0, you're out, something like that. You move on to like you do or you don't move on to the next round of interviews. Yeah, so the bulk of the paper will be the method section. This is laid out pretty nicely. The data set, I just want to make sure that it's linked here. I know it's in the GitHub. I'll just grab it there. This is the data set, and they actually outlined it pretty nicely. You can reference the website itself. I'm not sure if it has, right here, this data set. So you should probably reference this paper. But this summary is nice, so you can paraphrase this summary.
So would the implementation and like future uses, would that be included in results or conclusion?
Implementation?
When
you say
like not implementation, the limitations of like our model and our research.
Yeah, you should include that would go into here. Conclusions.
It's like a subcategory there.
I would actually argue that you should have a 7th section here for limitations and future work.
And then that could like go back to the motivations that we originally talked about.
Yeah. How can we get closer to meeting our motivations? Satisfying motivations. The general idea is that something that works most of the time, not all the time, not something that is absolutely correct, like an algorithm, but something that is so often, yeah, sure as hell. Yep, that's it. That's a heuristic. And yeah, so like the gender, ethnicity issues would go under the ethics and biases. See, this paper is, you could paraphrase directly from this. That's what I was actually planning to do. And I think the paper that used the similar data set did the same thing that I was reading earlier. Pre-processing, this would go into the steps. So we would have a category for imaging. We reference pi radiogenomics, because that's that's the library we used. RNA sequencing, and then the clinical data. Something else we need to do in the background is talk about maybe introduce. So in the data set, we should introduce what all the modalities are. So, you might ask, what are CT? What are RNA sequencing? And then
And these are the places where you can like literally bombard with citations and references.
You don't have to go into like the history. You just have to talk about like what it is, what features are relevant,
how it works.
How it works, and what features are relevant. Relevant features, yeah. Segmentation, this goes into the pre-processing, I think. I'll just move that there because we used lung mask. If you look up lung mask on Google, I'm sure you'd find that repository I used. It was really easy to use, actually. Feature extraction, I don't know if that, yeah, okay. Feature extraction and correlation, that's more with what Alex has been setting up. Model implementation, this is referring back to the models we talked about in the related work and motivation. And then the metrics would just be the specific metrics if we're looking at like precision recall, accuracy, F1. Results, I imagine what we're going to have is we're going to have a table of results for each method. So table of metrics for each method. And I think it should follow with a like an explanation for why the best performing model was the best. Ethics and biases, I think that maybe some other people will have more ideas for what we can do there, but incorporating the gender, maybe also risk for PHI leakage, something like that. Conclusion, overview from the abstract. Sorry, usually what people do is they reword the abstract and make that the conclusion. And then the limitation in future work is just how can we get closer to satisfying our motivations. We did not very many samples, maybe a call for longitudinal studies, radiogenomics data, to just exemplify the need. Because if someone's reading a paper and they say, oh, if someone who's trying to, write a grant for longitudinal radiogenomics study, they'll see our paper, they'll cite it. So that's kind of the goal. Yeah. So what we did now is we've taken the outline that was pretty general and we've expanded it such that it's more specific to what we need to do. It's a lot. I would definitely start, like, for people who want to learn. So the tasks can be split up based on where your interests are and what you want to learn. For people who are more interested in the medical stuff, I would say go for the related work and motivation for studying non-small cell lung cancer, right here and right here. For people who are more interested in machine learning and AI, who want to learn more about the field, talk about what has been done in radiogenomics with machine learning and, you know, those models that I mentioned here. I mean, you can look up plenty of YouTube videos, I'm sure. There's plenty, and there's plenty of papers you could read too. For people who want to learn more about, who are familiar with machine learning but want to learn about more novel segmentation and feature generation, you know, you can go to Pi Radiogenomics, which is the package I use, or you can look at this right here, which is the lung mask. Let's see if I can find it right here. Got a question. I noticed that the data set includes time to death. Yeah, Abby, I know what you're saying.
Yeah, because you said last time it could be so many other reasons since most of our patients are older.
If you look at the distribution, they're like what? The median's like 85 or 80.
I think the median is more like 60s or 70s, but yeah, there's a lot of other different reasons.
Yeah.
Ethan, something I read, I was concerned about this. So I actually met up with this clinician and I asked him about this, that we have this whole data set and it has a column for death, but the reason of death is not given. So he said that when a data set is made and if a death column is there, the reason is cancer. That's why there is a death column.
Okay.
They won't give you a random death column with any arbitrary reason. It is there because it is caused by cancer.
Okay, that's good.
Yeah.
So we can look at, you know, whether they die from cancer or whether the cancer reoccurs, or, you know, either one or both at the same time. The end. So sometimes I work with traumatic brain injury, and the problem that we have is that the endpoints are really poorly. The clinical endpoints are poor. You mean we only really have death for
What?
TBI, but
Okay.
for this cancer we have reoccurrence, and with TBI you really don't have reoccurrence of TBI. It's very difficult to measure secondary brain injury, but it's very easy to measure the reoccurrence of cancer. So we could use either or, Abby. That's a good point. And then for people who are interested in, you know, the ethics and biases, you could reference papers that talk about this and why it's important. You could look at what PHI there might be in CT imaging, because while CT imaging is, you know, it's like black and white, there might still be some data that lurks in there. And yeah, we're really doing it. Anybody who wants to help out with the software side, let me know, because that's what I'm focusing on. Just to recap, we really have a couple main things done. I'm waiting on, so this function, Alex, this is reserved for you, right?
Yep, I'm working on that. I'm just having problems with the time series part. Other than that, I'll get it in there committed.
Yeah. So we have a couple things. We have these functions are all for calculating about 160 features on the imaging, on a single image. We have a function that segments a single lung image. We have a function that processes the RNA-seq data. We have a function that processes all of the data. And then this is the function that processes all of the imaging data. In here, I still have to specify which image you're going to use in the results. So right now it's doing it for all of the images, but we want to do it for, we want to have features only for the most, let's say top 5 most representative images for each patient. And they all have to be CT scans, and all of those patients have to be, they also have to have paired genomic data. And then I have some functions for running random forests. Like running the models is the least important part of all of this. It's really the least important part.
It's Python, like 2 lines or 3 lines.
Yeah, Python has made it very easy to do it. But these models are relatively simple. I haven't added any parameter or hyperparameter or grid search, which we should do. There's very little we can do on the machine learning side with this because we have very few samples.
Like modern day machine learning is just creating, then instantiating it, and then calling .fit and then .predict. That's all it is.
Yeah.
Just implementing. Then you can have machine learning in your title or of your article or whatever.
Yeah, but these models are pretty well studied, and that's not the novelty of it. And it'd be cool to use sparse coding because that's new. More novel, and I already have an algorithm from a project we did over the summer that finds sparse codes. So if I go to GitHub, or let me think. We have this is from the summer. We looked at model.py. This is, an algorithm that, calculates sparse codes using ISTA. ISTA stands for iterative sparse something for sparse coding. A quick question: why are we using the largest diameter sizes in the most representative images? That's a good question. So let's think about it, right? When you're trying to find, you want to pick the segment of the lung that is most likely to have the most cancer. If you're trying to evaluate cancer, right, you want to pick the segment of the lung that is most likely to have the highest proportion of cancer, and that would likely happen at the large part of the lung because it has the most volume. There's the most room for cancer to spread. Most of the image is important. It was mentioned in the paper that I read, so I don't know what other kind of heuristic you use to pick the features. I mean, I don't know that the features we have will hone in on cancer.
It just basically the largest diameter is taken so that not just you could see the tumor. So if this is the tumor right here, you want to see areas around it so that you could see if there's any edema or any other kind of like physical changes is coming to the site, and you want to see the necrosis and everything. So that's why you need the biggest chunk of the tumor to analyze. That's like one of the reasons.
Yeah, but we wouldn't be selecting based off the tumor size. We'd be selecting based off of the lung size.
Yeah. I mean, this is how we work in the brain. I've never worked on lung.
Yeah. Cool. All right. So I'm sure we can communicate offline about what specifically we want to do, but there's a lot of writing that needs to be done.
Yeah.
And then for people who are, less interested in the writing, we are going to need figures to describe our workflows.
Yes. For figures, I would recommend each and every one of you to look up on journals, especially like good journals like Nature and stuff. See how they're making figures, and if you could make it on, I don't know, Adobe or something, that's good. Otherwise, I have this one website that I recently found. I'll share it with you guys, and it's kind of cool. They have multiple templates that you could use. So I'll share that with you.
I'm a big Sorry. What were you gonna say, Alex? Alex? Okay. I'm a big minimalist, so I make all my figures on PowerPoint. It works for me. It's worked for me for a while. This is a very, very minimal figure, but it just shows an example sample, which is just a region of time series, and it shows the general framework that was used in the paper.
But like if you have a good graphical abstract, so I mean, if you're shooting for a big project and we are hoping like, you know, to good throw it in a good journal,
Yeah,
I think we should, you know, go for a big one.
what is
Like, wait, you're not. Also, tomorrow when I'll be speaking to Dr. Paul, I'll see if he could, you know, give some of his students to work with us and they could work on the paper, because that would be interesting.
Yeah. Yeah. So the figures are also a good, important part. And just to give you an idea of how important it is, my PI at the Children's Hospital, he starts writing a paper by creating figures. So he does the figures first, and then he does the writing. We're doing writing first and then figures, but most people do it the other way, just because that's how important the figures are. You're having good figures increases the likelihood that it'll be more reachable by people. It increases the reachability of the paper, because people go to the figures first because they want to see drawings.
Yeah.
Like picture books, you know. Yeah, cool.
Also, what kind of tables are we gonna build?
Probably for results. We'll have a table for results. I mentioned that in.
We could have a table for all of the features we have, like the top features we have. Not
Like feature importance.
Yeah, either we could have a correlation map, or we could have like a semantic graph, or we could have like a whole table, like 3 options.
Yeah. And then, yeah, we're gonna want a figure for that, the correlation map.
When will you be done with all the images, like, so that we could make a correlation?
I can work on it Friday,
Okay,
and I'll just send you.
because there's this library which is like pretty easy. So once all the data is in there, you could make a semantic graph.
Yeah. Cool. That is the plan. I feel like we have a good grasp. Does anybody have any questions about the paper, about tasks?
I mean, I was gonna ask a couple questions regarding the clinical data, but let's see if anyone else has any questions first.
Yeah.
I was just gonna ask a question about if we're gonna meet anytime this week, like maybe Friday.
Brandon, you got a question?
Yeah. Brandon, you mean like with a smaller group?
Yeah, just like
Yeah.
or just like collaborate for that.
I think this Friday I can. I don't think anybody was available last Friday, but
No.
we'll likely be able to.
Okay, just like in the Slack or something.
Yep.
Okay, awesome. Thank you.
Got it. Question. Where do you advise us finding the papers to cite, especially the sections on the actual machine learning? Yeah, so
Okay.
Scholarly sources.
yeah.
Okay, so let me share my screen. Also this is like one of the templates I was kind of trying to make for the project, like this kind of thing, which looked kind of okay-ish, cool. It was like more for a graphical abstract. But so if you want to go to machine learning, one of my top preference would be like, you first go to the Google Scholar, you Google Scholar, and then you find papers like you say deep learning in say lung cancer, and then you could say different names of like journals which are really good. So maybe you could say nature, right? And then you would find all these papers. So this is from Nature Med, which is a really cool journal. And then, oh, this is kind of cool.
You can get lost in papers.
Okay, yes, we're not reading right now. So, so like this, you could go here, and if you don't know how to cite papers, so you go here, say you want to go here, and you go to BibTeX. This is what we use when you're working with LaTeX. You just click here. You copy this whole thing, right? And then you go to your paper, you go to reference.bib, and then you paste it. Don't bold it, just paste it. And then whenever you're gonna cite it, so it's like this name. So when you go into your main tech file and say keywords introduction, so say here introduction. So if you want to cite anything, you hit / cite, and then this would come up right here. So if you compile, you will find it. Where is it? Where's introduction? Right here. Why is it saying a question mark? Oh. Compile. Why is it a question mark? That's why I hate using templates.
Did you import this? Did you import the citations? Did you import references.bib or?
I have this whole file here. Okay, I'll work this out. Maybe it's not set it up yet.
Yeah, you have to sometimes import references.bib. Otherwise, you'd have a bibliography in the bottom of the text file.
No, it's not here. I think there's something messed up in the style part. I'll figure that out.
Cool. Yeah, but that's how you go about finding citations, finding references, and then adding them. Cool. If there are no more questions, Alex, do you want to talk? Sure,
Yeah.
Brandon. Yeah.
Brandon. Easy left. All right. I'll share my screen really quickly. So which side? Wrong side. There we go. So referring to what Abby mentioned earlier, so we have actually a quite precise time to death days and I'm assuming we're going to use that as one of our 4 target variables. So do we want to bin this like I did for the, oh yeah, I did bin in the data recurrence as well. So it's based on the span of a decade. Do we want to do the same thing for time to death though? Because I personally don't think so, because we don't have enough data to be as precise for time to death.
Yeah, so you want to create bins, so it's more of a classification problem.
Yeah, I agree. I just wanted to hear his thoughts, but yeah,
that's fine.
I agree as well. That would be regression though, if we we're predicting exactly which date.
Yeah.
Right. And then where is it? Okay, so I have part of the correlations done, and I just wanted to make sure the format's okay. So I'm just I was gonna send it to you in a correlation matrix right here. Actually, let me open it over here. So this the correlation matrix here. I just wanted to, obviously it's not the most readable because I need to clean up some, like remove some things. I could remove anything that's like less than 50% correlated. But here's just a couple of the things. Just for example, pack years is the most correlated with the smoking years, which quit the year they quit smoking, which makes sense if you think about it, because pack years has years in the equation, so they're proportional.
Yeah.
So that makes sense why they're positively correlated. And then there's also pack years.
Can you make positive blue and negative red?
Positive blue, negative red. That probably makes more sense. Yeah.
Red bad.
Red bad, or yeah, I could do green or red or blue or red.
Yeah.
But pack years and the patient's weight are also like somewhat correlated. I would say that's so far because I've been having problems with time series stuff, so I have to finish pre-processing that. But
So high correlation to me is like 0.8. I wouldn't filter anything below 0.8.
0.8, that makes sense because it's more noise at that point.
Yeah, because 0.54 still means there's about 0.5 or 0.45 that isn't explained by one of the features.
That's like random at that point would be also better. Yeah. But yeah, that's what I wanted to show there. I will fix that up. And also for after I get all the data pre-processed and I added in the commit for Git, do I want to tell you the feature importances as well? Because that would require me to like do some ML estimator stuff. This would be before we use Sapphics transformer.
Yeah, I don't know if we want. I don't know. I usually the feature importances. The way I see it is if I use a model, I want the feature importances to come from that model. I don't know if I'd filter based off of the feature importances from a random forest model if it isn't performing well. If it's performing terribly, then I don't think I'd rely on that as importance. I think that's a artifact of some other underlying issue. If the transformer had feature importances, then we'd report on those. I think.
Yeah. And I don't know if Safik mentioned, you already I think Safik mentioned the transformer, but did you have like this specific one yet? Or did you have like the class of transformers?
Bumblebee,
Yeah.
Optimus Prime.
More of an Optimus Prime, yeah.
It'd be kind of cool if they were named after Transformers. Like, I think that would be really, really cool.
That would be cool. We are using a Decepticon for this.
We are using a Decepticon Transformer.
That would be fun.
Yeah, but do you have any in mind?
No. I think I saw the Keras package. I was pretty happy with it. I still have to look it up. I'll look it up tonight after my maths homework.
Yeah, cool.
Cool.
All right, that's it for me.
I mean, we're doing pretty great on the project, to be honest. I didn't expect that.
Sorry.
We're doing pretty great on the project.
Yeah, we're not doing terrible.
Yeah.
Considering it's like midterm season and everyone's busy now, I think we're moving along.
Yeah, it's going swimming.
I mean, we still have to write the paper, so
yeah,
we haven't started yet.
Yeah. After in a week and a half, I'll be really free.
Yeah, I'm pretty sure by the end, like till December 1st week, like most of the paper would be done, but some would be left, and Ethan would send a message that can you please look up these sections and could you please help?
That's what happened last time. I'm going to Chicago next week for
really?
Yeah, for a trade show. We're showing the medical device I've been working on in the company.
Wow, that is so
doctors.
cool.
Very excited.
I'm going to New York in December.
Cool. Conference?
Yeah.
Cool.
So they're like giving free stay and stuff. I'm like,
nice. Okay. Anyway, that's it for me. I will see you guys later.
Yeah. Also, Alicia's coming to Philly this weekend.
Cool.
Yeah, so we gotta meet.
We can. I'll be around.
I'll text you.
Peace.
See ya. Bye-bye.